So again, any two conductors can be considered a capacitor. And they are a capacitor because once you take a charge from one of these conductors and place it on the other, an electric field will be created. And that electric field stores the energy that the capacitor now has. Now, the energy in a capacitor comes directly from the work done moving the charges. That's where the energy comes from. So in order to move that one charge from the first capacitor to the second capacitor, took a certain amount of work. The next charge is going to take even more work because an electric field is there. And that will continue to happen, that the more charges I try to move, the harder it's going to be to move each charge. But when I'm done, the total amount of energy required to move those charges is now stored in the capacitor. If I want to discharge the capacitor, all I have to do is provide a conducting pathway that will allow the charges to flow back to their original neutral condition. Remember, because the moment a conducting pathway is here, the charged particles will be pushed due to the electric field that exists between the two conductors. And the flow of those particles will dispel the energy that was stored in the capacitor. Michael?
Which way does the electric field face the direction that you move the electron, or is it the opposite way?
The electric field is always going to be away from the positively charged device and towards the negatively charged device.
So the one that you take the negative charge from, that's the positively charged one, right?
Yes.
Okay.
Now, I must state this for the record, that we have to be able to talk out of both sides of our mouth a little bit here. Only electrons actually get moved. That's the reality of circuit design and of conductors and all of that. But we will often talk about the motion of charged particles as the flow of positive charge, because everything in electronics about the flow of particles in circuits is positive charge flow. So we're constantly talking out of both sides of our mouth on this. So everything about the flow of particles in a circuit is about the movement of positive charges. But we know that that's not true. It's the motion of electrons, which are negatively charged. So we have to constantly switch back and forth there. The truth is, it doesn't make any difference whether we talk about the flow of negative charges or the flow of positive charges. The amount of work done and everything is still the same. So, once you establish this conducting pathway, charges will flow back until the system is equalized again and the electric field is returned to zero. That's the basics of a capacitor. And like I said, any two pieces of metal can be considered a capacitor. Now, what we would like to do is find a way to increase energy storage in the most efficient manner possible, meaning finding conductors that are shaped in such a way that we store more energy for the amount of work necessary to move the charges. In fact, this is how we are going to define the capacitance. You see, just having two chunks of metal doesn't mean it's efficient to move the charges. There might be more efficient shapes. So we define capacitance, and you're going to hate this. The symbol for capacitance is a capital C. And yes, the unit for charge is a capital C. I know. But we state and define, so that's 3 lines for my equals here, not 2. This is a definition of capacitance. So 3 lines means defined as. This is a human-created measurement, and we are defining this term as the charge moved per applied potential difference. This is how we will define capacitance, as the charge moved per applied potential difference. Something with a high capacitance will allow lots of charges to move for the same potential as an object that has low capacitance, which will allow fewer charges to move for the same potential. Meaning we say that something has a high capacitance if it moves more charges per volt than another object that moves fewer charges per volt. So we try to find arrangements of conductors that allow more charges to be pushed for the same voltage. Now, there's a lot to unpack here, but there are some big things I want to make sure I throw in front of you before we go any further about what this means. First, I think of a capacitor as a bucket that stores charge, because that's really a good analogy here. The bigger the bucket, the more charge it can store. So a big capacitor is a big bucket. It will store a lot more charge than a small capacitor. And if you think of it that way, you think of it as a storage of charge, it will help as an analogy for later. So the bigger your capacitor, the more charge it can store. Now, saying that doesn't really give you an idea or an impression of why that's valuable. But the movement of charge and the storage of charge has incredible value, because charges can do work. When a charge moves from one place to another, it can do work. It can do lots of things. So the ability of an object to store charges for later use has incredible value. And that's the other thing. Once a capacitor is charged, it remains charged indefinitely until you need that energy back. It's like creating a place where you can put things really high so that they store gravitational potential energy. Except you can walk around with this in your pocket. Because once you store the charge on the capacitor is charged until you need the energy and will stay charged indefinitely. Meaning the charges, unless there's a pathway for them to go back to where they were, your system remains charged until you need that energy. Capacitors are amazing batteries. They're amazing ways of storing electrical energy. And that's what they are designed to do. In fact, that's how we use them. How many of you have a system in place that will allow the power in your computer will stay powered even if the electricity outside your computer turns off? Meaning, how many of you have one of these surge protectors and power adapters that's designed to maintain power to your computer even if the electricity fluctuates outside? What do you think is storing the energy in those devices? It's definitely capacitors. Anybody hear them huge thumping stereos outside and they're getting all that power from the 12-volt battery in their car? No, they've got capacitor banks in line with their amplifiers to ensure they have lots of power for when the bass drops. That's what they're doing. They're storing the energy in the capacitor. In fact, there are huge capacitor banks in places like Fairbanks, Alaska, that are designed to maintain power for days, even when power is interrupted due to snowstorms and blackouts and stuff like that. Capacitor banks are excellent ways of storing energy. Yes? Conversation yesterday, we talked about generally what a capacitor is, and I want to reiterate it. A capacitor is just any two pieces of metal, because it is any two pieces of metal that are not in contact have a capacitance. However, if you just have two chunks of metal and you let them sit around, they don't necessarily store energy on their own. In order to store energy, you have to do work on the system to move charges from one piece of metal to the other. And then to get back that energy, you have to provide a conducting pathway to allow the charges to flow back to their neutral position. And it is the flow of those charges on their way back where you can capture the motion of those charges to do work. The thing that is missing in a lot of this conversation is what you can do with the flow of charged particles. That part's not being discussed because the flow of charged particles is current, and how current can be used to generate any number of things is being left out of this conversation. So we're basically talking about lifting up a bunch of things and putting them up on a shelf, knowing that once they're on the shelf, they have energy, but with no idea how useful that energy might be when the stuff falls off the shelf, which is really what we're talking about. That's what a capacitor is. It is the lift hill of a roller coaster. That's what capacitance is. So you get all the roller coaster cars to the very top like SheiKra, where they can sit up there for a bit, and then collapse it down, put it in your pocket, take it someplace else. Because you can take a capacitor wherever you want and set it up and then use the energy that's there. That's what's kind of amazing about them, is they store all that energy in a very compact size and space. So what we're going to do is we're going to talk about the first part today, and that is, how do you create a organized capacitor? Something where we might be able to figure out how to ramp up the capacitance. And then we're going to talk about the usefulness of it as a circuit element device. So first, yesterday we talked about the fact that we defined capacitance as how much charge you can separate with an applied potential difference. I want to say that again because I don't think that you guys got that clearly yesterday. The definition of capacitance is how much charge you can separate per volt of applied potential difference. It's a bucket that stores charge. So a capacitor with a large capacitance stores more charge per volt than a capacitor of lower capacitance. The bucket's bigger, can store more energy. And so we say it's based on the applied voltage. That's how we define capacitance. So how much charge you store has a usefulness. But more importantly, we tend to look at this from another standpoint then. Once we know something's capacitance, we can use it as a function to figure out how much charge has been stored. So although this is a definition, this is a function. When dealing with circuits, we'll often use this functional equivalent to talk about the amount of charge stored on a capacitor. Now, staying with our discussion of definition, let's also recognize that there is a unit here, which is coulomb per volt. I'm writing out the coulomb and not C per V because I want to remind you that capital C stands for capacitance, but capital C also stands for the unit coulomb. You will have to understand the difference. We have a name for this called the farad. After Mr. Farad, I guess. Maybe Ms. Farad, I don't really know. Maybe non-gender specific Farad, just some person who is named after. I know nothing about them. So I will say this though, that a 1 farad capacitor is a huge capacitor. You know, it stores a coulomb of charge for an applied volt. Now, let me be really clear. I don't know that you could charge up a 1 farad capacitor with a AA battery. A AA battery is 1.5 volts. I don't think a AA battery has 1.5 coulombs of charge that can be moved. So just because you have a capacitance doesn't mean you can necessarily charge it fully. It's just telling you how much it can hold under those circumstances. I have some 1 farad capacitors in the back that we will be using for an experiment. Those are huge. Generally, most capacitance tend to be in the microfarad area. So microfarad, 10 to the negative 6 farads. Picofarad, 10 to the negative 12 farads. Those are really common sizes. Oftentimes with capacitors, they can't print micro on the enclosure. So sometimes you'll see microfarad printed as MF, which doesn't stand for what you think it does. Millifarad stands for microfarad in most uses, even though the lowercase m is supposed to be milli. And sometimes you'll see farad, which is another way of saying picofarad. All right, so these will be stamped on the capacitors or to issue their size. Most capacitors that you'll be in contact with are going to be in the microfarad range. And so that's the kind of the range we'll tend to use. A lot that we have in the back. But microfarad is really small. And most of the capacitors we're going to see, or to get some real effect, are bigger. So I do have a bank of 1 farad capacitors we're going to use for some laboratories. because you can actually see the value of their capacitance. When the capacitance gets smaller, it stores a lot less energy. So you might wonder why we have them. It's going to be clear why we have capacitors once you start looking at them in circuits. Now, just a brief, quick overview. We will be making circuits with capacitors. So when it comes to circuits, there is a set of standard symbols we're going to be using for these circuits. And your book tends to have a variety of different symbols. I want to make sure that we've seen at least a few of them as we get started with this. These symbols represent voltage sources. Or potential differences. Or batteries. And we use the same symbol for most of them. It is not terribly common, but they have done it where they'll just have a black box and say 1 voltage potential difference or something like that. But generally we use one of these symbols to indicate potential difference. The truth is these symbols here are the symbols for a battery. The first one here is a single-celled battery, one pair of long and small lines with basically the small line is the anode and the long line is considered the cathode. The multiple pairing would be a multi-cell battery. So there's multiple sets of cells. A single voltaic cell produces a certain amount of voltage based on the choice of metals and acids. It's come to my attention that you guys aren't building batteries in chemistry any longer. So if you've never built a battery, I have some voltaic cells. We could build some wet cells in here so you can see the process of building a battery, generate a couple of volts. They're not particularly exciting, but they used to do it in chemistry, so I could count on you guys having done it. Have any of you built a battery before in chemistry or AP chemistry? So it's not part of the curriculum any longer? So it's appropriate. We'll build one. I'll have Mr. Schwartz or Mr. Miller get me the acids that I'm going to need. We're not going to use anything special, but if we do build a battery, actually we might go to a different lab to do it. Someplace where we have the curtains or the aprons and the goggles. I don't have those for my labs, but if we're going to work with an acid, it would be appropriate. And I'd also have to have you sign the Flynn safety contract before we do it. But who cares? It might be fun to build some wet cells. We won't use them in the lab because they're inconsistent and they'll run out pretty quick. So we tend to use dry cells. But generally, I don't think you need to have the history of batteries here. A battery provides a potential difference. And so when we use batteries as a symbol here, we're using that as our potential difference in our circuit. It's appropriate that you understand that the positive side and negative side of the battery are fixed, and they don't necessarily determine the direction of current, but they do determine the direction of an increase in potential. So this direction on this symbol is an increase in potential. So there is an increase in potential from going from A to B and a decrease in potential from going from B to A. It is up to you to be aware of that. Now, capacitors, there's a lot of different kinds of capacitors. So because there's a lot of different kinds of capacitors, there tends to be lots of different symbols. We will only see 2 kinds of symbols for our capacitors. These are the 2 symbols we'll see for capacitors in our class. And we don't see the one on the right as much as the one on the left. The one on the right is an electrolytic. And the one on the left is just a generic capacitor. So the one on the left could just be 2 pieces of metal close by. The one on the right, the electrolytic capacitors are in a solution, and that solution has been designed to increase the amount of capacitance that you get. So electrolytic capacitors are polarized and must be connected in such a way that the positive side of the capacitor is connected to the positive side of your potential difference. If you don't connect it in that way, you do not get the measured capacitance out of the device. You get a reduced amount. The capacitors we will use in lab are electrolytic, and so you have to pay attention. The ones we have will look like a little box. And that and have two leads coming out. One of the leads will be longer than the other. The longer lead is the positive side. The wires coming out of the capacitor are called leads. Yes?
Do they write the plus and minus on the side, or do we just assume it?
Most of them have them on there. In fact, I don't think I have a bank of capacitors that doesn't have, if it's an older round capacitor, because I have a few that are in the millifarad range that are like round like this. They look like little, cans. And they'll have two wires coming out. They'll have a stripe on one side here, one of the wires. That stripe is the positive side. And usually it's got a lot of plus signs on it, so it's pretty easy to tell. But they get handled by people, and some of that stuff wipes away. So the wire length, the lead length, is the other way that you can tell. So I bring this up because our circuits are going to be things you'll have to construct. And understanding how a circuit diagram is set up is how our circuit is going to behave. So although there are other symbols, and you'll have to learn most of the ones that are going to be in our setups, understand that circuit diagrams, by their nature, are supposed to be efficient ways of demonstrating how a circuit is organized and how the parts of a circuit are relevant to each other. So this is a circuit with a switch, a voltage supply, and two capacitors. These capacitors are considered in series. Since you've had no electrical background at all, since it was removed from AP Physics 1, series simply means that the circuit elements are one after another. And I contrast that with a parallel circuit or a parallel element. A parallel element will allow for a break in the circuit so that there's multiple pathways from one side of your potential difference to the other. So here is a series circuit. Here's a parallel circuit. A switch does exactly what you think it does. It creates the closed loop between your potential difference and your circuit elements. Opening and closing a switch opens and closes the connecting pathway. A circuit is not complete unless there is a complete pathway from one side of your potential difference to the other. Now, I'm saying that, but you should also know then that none of these can ever be a complete circuit. Because even if I close the switches here, the capacitors have a gap between their plates. That's the definition of capacitance. Two pieces of metal that aren't touching. So all capacitor circuits aren't complete circuits. They are not complete. So there's no flow of charged particles in any capacitor circuit. That's an out-and-out lie. But you have to understand that there is a truth in that lie. And let me explain why. A single potential difference and a capacitance connected in a circuit. Even with the circuit element closed, this is still considered an open circuit. It's open because there is a gap from this side of the plate to this side of the plate. No charged particle can go across that gap. However, that doesn't mean that current doesn't flow in this circuit. The negative side of the battery is electron rich, and the positive side of the battery is electron deplete. Those aren't fancy terms. I'm just saying the negative side of the battery has a lot of extra electrons, And the positive side of the battery is missing electrons, which means that our neutral capacitor, neutral meaning there's equal amounts of positive and negative on each plate, when subjected to the potential difference, will allow negative charges to be pulled off of this plate and deposited with the battery. The battery is a pump. So the battery has acid inside that will eat away at a piece of metal. And when it does so, it will take that electron and cycle it around to the other side of the battery. Adding an electron to this side of the battery allows an electron to flow from this side into the capacitor on that side. Now, this occurs because the capacitor, being the way it is, being the way it's structured, allows for a potential difference to move charges from one side of the capacitor to the other. So that over time, charges are going to build up on the capacitor, making the top plate of the capacitor the same charge as the top plate of your battery, and the bottom plate of the capacitor the same charge as the bottom plate of the battery. So the capacitor will be charged in the same way that the battery has separated charge. Charges will flow until the capacitor reaches its maximum capacity to hold charge. The amount of charge a capacitor holds depends on the applied voltage. So this flow of charges doesn't happen instantaneously. It takes some time for the charges to be pulled from one side of the capacitor plate and deposited on the other. Now, how much time it takes is a story for a different chapter. But the charging of a capacitor will take some time. It can be milliseconds or hours, depending on the arrangement of your circuit. But ultimately, you'll reach a state of equilibrium where we cannot pull any more electrons from one plate and put them on the other. Basically, what happens is the electric field inside the wires decays as the charges separate, but builds up in between these plates. Now, this, although it's based on the definition of capacitance, this is the function that defines how a capacitor will be charged. And there's several things about this function we're going to use over and over and over again. So although it's based on the definition of a capacitor, be aware the charge on the capacitor is wholly based on the size of the capacitance and the size of the applied potential difference. And it's a straightforward linear relationship. You double the potential, you double how much charge you're going to get in that capacitor. A capacitor's ability to contain charge is without boundary in ideal circumstances. Meaning I could apply 100 million volts, and this capacitor will hold whatever amount of charge it's supposed to under 100 million volts. Now that's actually not true. All actual capacitors are rated. So there's a difference between ideal capacitors and real capacitors. And this is true for every kind of circuit element. There's what the circuit element is supposed to be able to do under ideal circumstances. And then there's what the circuit element can do under real circumstances. Ideal capacitors can hold any amount of charge you want and can have any applied voltage applied to them. They will hold that charge indefinitely without leakage, meaning forever. Real capacitors, not so much. And although we're not tested often on the difference between real and ideal capacitors, we are tested on the difference between real and ideal circuits all the time. So it's important for us to understand that. So for every circuit element that comes up, we'll eventually have a conversation about real versus ideal. Batteries, resistors, amp meters, voltmeters, all of these things have their real performance versus their ideal performance. Real capacitors are rated so that there is a maximum voltage to which you can't exceed. So every single one of them will say, do not exceed this many volts. So if you look at a capacitor, it'll say, 12 microfarads at 6 volts. That means that this capacitor is good up to, but not to exceed 6 volts. If you exceed 6 volts, actually the consequences are bad. Because what's not being discussed here is that in between these plates, an electric field is developing. And in most capacitors, it's not an air gap. There's something between the plates to keep them from touching each other. Usually it's an oxidized material, but there's something between the two plates. If you continue to increase the potential difference, you're going to continue to increase the size of this electric field. It is possible you can create an electric field so strong that electrons will begin to jump the gap from one plate to the other. They'll just jump right across. But they don't just jump right across, they tend to spark right across, igniting whatever's in their pathway from one side to the other. Mysterious blue smoke will begin to emit from your capacitor. And that's when you know you have exceeded the threshold of your capacitor. So if you've ever turned something on, heard some kind of crackly noise, and saw blue smoke escaping, you now know what probably happened. You probably fried a capacitor. They are the number one component to go, especially as a power supply begins to malfunction in a computer or in your game machine and stuff like that. It is the capacitors that tend to be the things to go first. And trust me, do not inhale the blue smoke. You will be unhappy with the results. Yeah?
Is it blue because of the chemical burning?
Yeah. Generally. And the dielectrics that they tend to fill these with and the electrolytes that they fill these with are toxic. So if you see the blue smoke, it can kill you. So please stay away. It's usually pretty bad, or it's usually a carcinogen. So generally, whatever the power rating is, you can't exceed it because it creates an electric field too high. Now, this is the basics about capacitors and how they're going to look in our circuits. They store energy. But to understand the rest of this is to understand how you make a capacitor. What's actually in the little box that is storing the energy. And we are only going to talk about 3 different kinds of capacitors, but there are lots of different ways to make capacitors. Lots. But we don't use anything but 2 different ways. So although there are 3 different kinds of capacitors in general, the only ones we ever see are parallel plate ones. They are the most common style of capacitor. Next, we do have some that are cylindrical. Most cylindrical capacitors are capacitors by accident. And I'll explain what I mean in a minute. And then last are spherical. Spherical capacitors are interesting in that there's a lot of things that end up being spherical capacitors, not because we want them to be, but because they fulfill the requirements of a capacitor. The Earth is a spherical capacitor. It stores energy in the same way a capacitor does, even though it's not metal necessarily, and there's no other plate laying around. So each one of these can have capacitance. It'll be your responsibility to be able to figure out how to calculate the capacitance of each of these devices. You see, capacitance is a physical measurement. The size and shape of the materials determines the capacitance. Again, capacitance is a physical measurement. The size and shape of the material determines the capacitance. So, although yes, these 2 Hershey's Kisses, by definition, form a capacitor because they are wrapped in metal and they are separated by some distance, there's no way to actually calculate ahead of time the capacitance of those 2 kisses based on their shape. Now, I could apply a potential difference to them and measure how much charge is applied to them, and that would be an experimental way to determine their capacitance, but that would be ridiculous. What we want to do is find a way to predict the capacitance of a set of materials based on their shape. And so we will have to use each of these 3 in terms of their shape and their size to figure out how much capacitance they have. Parallel plate ones are pretty straightforward. They sound exactly like what they are. It's two sheets of aluminum foil very close together. Parallel plate capacitor. So they are designed exactly as they sound. But they would be too big to actually make capacitors. So generally use a strip of metal, put another strip down, and roll them up. And that's what we have. So they're like a giant Swiss roll. And that is how almost all capacitors are made, which is why they all look like little cylinders. Because they are just two pieces of metal that have been rolled together. Now, to get smaller ones, we just put actually two little pads together and separate them with the material. But it's our responsibility right now to talk about how you figure out the capacitance of a set of materials. Definition. Capacitance is charge divided by potential difference. This is how you determine the capacitance of a device. You charge it up and you measure what the potential difference is once charged. I know it seems like a little bit in the reverse, but we're going to do this once and you'll understand how this tends to work. So let's start with a parallel plate. And I'm going to draw this in 2 dimensions because it's the best I can do. Parallel plate must have 2 uniform plates. So my parallel plate capacitor has 2 plates that overlap. Now, when we talk about parallel plate capacitors, there's a lot of things here that you have to understand. We're going to fake it for this. A parallel plate capacitor, we are assuming several qualities that are actually not true. First, parallel plate capacitors, we assume that the plates are very big compared to how far apart they are. That is not this picture. Does everyone understand? When I say 2 sheets of aluminum foil, I'm literally talking about 2 sheets of aluminum foil as big as your tabletop and separated by a single piece of paper. Very big compared to the separation distance. What this allows me to do is say that almost all of the electric field is contained in places where the electric field is uniform. And very little of it is near the edges of the plates. So I'm trying to say that when there's electric field in here, assuming the top plate is positive, most of the electric field between them will be uniform until we reach the edges. And that there's not very much edge space compared to the amount of overlapping uniform space. I know that's a lot of rules, but please understand there's a reason why I'm trying to be like this. So I'll say it again. When we talk about parallel plate capacitors, the first thing we say is that they have a lot of surface area for very small separation distance. So there's a lot more areas where the electric field is uniform and very few areas where there are edge effects. We're going to say that each plate has area A. So it doesn't really matter whether these are circular plates or square plates or rectangular plates or triangular plates. They just have an area A and a separation distance D. We're also going to state for right now that inside between the plates is a vacuum. It's 1 C and 2 U's, right? So we're talking about a vacuum. So there's nothing between the plates, no gases, no dielectrics, no materials. We're going to talk just about a parallel plate capacitor where the inside is just a vacuum. Now those are really, really hard to make. You have to keep the plates apart without them touching.